Welcome to ePadasala lecture series in computer science. We are going to discuss about greedy approach. Last module we introduced some of the basics of greedy approach and we discussed some examples of greedy approach. In this particular module we are going to discuss about the minimum spanning trees. So, the learning objectives of this particular module is to review some of the fundamentals that we introduced in the last module, that is the greedy approach. Then we are going to discuss about the minimum spanning tree, one of the most important problem in computer science, and we are going to discuss about two greedy based algorithms for finding the minimum spanning tree, that is Prim's algorithm and another is the Kruskal algorithm. So, last module we have introduced the concept of a greedy approach. So, let me recollect what we were discussing. There are many problems where we have to take sequence of decisions. Greedy algorithm always takes decisions that are considered to be the best as of the present moment. In other words, the greedy based algorithms are locally optimal. Normally greedy algorithm works, but occasionally it may fail also. Sometimes it may not give the optimal solutions, but instead it may settle for some near optimal solutions. As we said in the last module, greedy algorithms are much more faster. Therefore, we consider this as a useful strategy for solving the optimization problems. So, the optimization problems are supposed to satisfy these two properties. One is the greedy choice property. So, that means we take lots of locally optimal decisions, and when we try to combine all these locally optimal decisions, we are getting the global optimal solutions. And similarly, the optimal solutions are considered to be the sequence of solutions that are considered to be the optimal for solving the sub problems. So, the main objective of this particular module is to introduce the concepts of spanning tree. So, let us review some of the basic definitions that are required in order to understand these two algorithms. So, connected graph means every node is reachable from every other node. Undirected graph means edges do not have any associated direction. Then spanning tree is a tree that is connected acyclic graph which contains all the vertices of the given graph. So, the objective of the minimum spanning tree is very simple. We will find a spanning tree with the minimum sum of weights. In other words, the input for the spanning tree algorithm is a graph. So, what we are trying to do is we are trying to generate a tree where all the vertices are available, but we ensure that cycles are not present in the spanning tree, and also we ensure that no node is isolated. So, the objective in short is to generate a connected acyclic graph that contains all the vertices of the given graph. So, the minimum spanning tree is the sum of the cost of the edges should be the minimum. If the graph is not connected, then there is a spanning tree for every component of the graph. So, we will take one simple example. So, let us take this graph as the input. So, you can see that there are 4 vertices. This is a connected undirected graph, because as we have seen in the previous slide, the edges are not associated with any directions. So, as per our definition, we should get a spanning tree where all vertices should be the present, but there should not be any cycle. So, these are some of the spanning trees of the graph. So, you can verify every spanning tree consists of all the vertices, and you can see that there are no cycles, and you can see that all the nodes are connected. So, this is the spanning tree. We can find a spanning tree by the brute force, but it is very complicated, as the number of nodes increases, the number of spanning tree also grow enormously. Therefore, the application of the brute force technique is not feasible. What is the practical application of this? Why should we go for these sort of things? In computer science, spanning tree is one of the most important problem which has got a wide variety of applications. Imagine like this, we are trying to construct a telephone network, then the pre-requirements is that all the nodes must be connected, but there should not be any cycles. So, that means the number of edges should be minimized. Translated to a telephone problem, it means that the number of edges reduced means the number of telephone cables are reduced. So, when the telephone cable is reduced, it leads to what is a saving of money. Therefore, not only the telephone network, any network that are related to power, telephone, etc., can use this minimum spanning tree algorithm to get a network where there is a connectivity, but at the same time there is no what is a redundancy of the edges. So, you can see that this is a undirected graph, and you have cost that is associated with each edge that is available. So, what is the minimum spanning tree? So, these are some of the possibilities. So, now you can see that this is one possibility, this is another one, this is another one. So, now you can see that the cost of this is going to be 4, this is going to be the cost 3, then this is going to be the cost 3. In other words, the cost of the spanning tree is the sum of the weights of the edges that are present. So, that means out of these 3 possibilities, the second and third one is very effective, because they are associated with the minimum cost. So, any spanning tree where we are getting the minimum cost is what we are calling as the minimum spanning tree, in short MST, or as some authors refer, minimum cost spanning tree, MCST, both are right. So, you can put everything into a nutshell. So, now you can say that a minimum spanning tree, MST, is a subgraph of a undirected graph, such that the MST includes all the nodes People refer this as spans all the nodes connected acyclic. That means we say that there should not be any cycles, and it should also have the minimal total edge weight. So, in other words, these are the pre-requirements for the minimum spanning. So, we will take another example. So, now you see on the left hand side you have a connected undirected graph, and on the right hand side you have what you say a minimum spanning tree, where you can see that all the cycles are removed. For example, there is no edge between A and C, because the addition of this edge may create cycle. So, you can see that this is the minimum cost spanning tree of your left hand side. How to construct this? As we discussed earlier, brute force is not a possibility, because for larger number of nodes, construction of minimum cost spanning tree is difficult. Therefore, we are resorting to the greedy approach. We will be using two algorithms. One algorithm is called Kruskal algorithm, where we start with no nodes or edges in the spanning tree. Then we are going to repeatedly look for the low cost edge or the cheapest edge, and we will try to add that into the spanning tree, at the same time ensuring that the addition of the edge does not create any cycles. In other words, the Kruskal algorithm considers only the edges. Other prominent algorithm is called the prime algorithm. So, here we start with any node in the spanning tree, and again we are looking for the cheapest edge. The criteria is that the new node should be an unexplored node. So, that means the node that is not belonging to the same subset where the source vertex is present. So, if any such nodes are there, then we are adding that. So, in this thing we not only look for the edges, but also the nodes. So, that means both nodes and edges are the important criteria for primes algorithms. Both these algorithms work for both weighted as well as the unweighted graphs. Both these algorithm works for both directed as well as the undirected graphs. In other words, there is not much restriction about the nature of the graph that should be considered as input for these algorithms. So, the generic algorithm, which is the common denominator of these two algorithms, can be written first, then we can branch out for each and every individual algorithms. The generic algorithm is like this: given connected undirected weighted graph G, the aim of this algorithm is to find the spanning tree with the minimum weight, that is going to be T. So, initially it is null, then what we are trying to do is we are trying to find the safe edge, and we are trying to add that into the set. So, repeatedly doing so results in the spanning tree. Fine. Based on this generic algorithm, we can branch to the first algorithm, that is given as the example of the greedy approach, that is the Kruskal algorithm. So, this is a photograph of Joseph Bernard Kruskal. So, he is an American mathematician, statistician and computer scientist who proposed this algorithm for finding the spanning tree. As we said earlier, this algorithm works with edges rather than the nodes. So, the algorithm involves two steps. One is sorting of all the edges based on the weight, because we are going to apply the greedy approach where we are going to look for the least cost edge. So, therefore, the first step is we are going to sort all the edges based on the edge weight. Then we are selecting the first mod V minus 1 edges that do not create any cycle. This is the informal algorithm. T is the empty spanning tree, E is going to be the set of edges, N is going to be the number of nodes in the graph. So, while T has fewer than n minus 1 edges, so we are going to remove the edge of the lowest cost, then we are trying to add that into T if it does not create any cycle. If no cycle is created, then we are going to add that, otherwise we are going to reject that. This is the Kruskal algorithm informally. This is an example. So, let us see how the Kruskal is applied here. So, now you can see that this is a undirected graph. So, you can see that the edges have weights. So, we have to sort. So, you can see that 1 is the minimum cost edge that is present, then we have 2, then we have 3, then we have 4, then we have 5. So, the logic is very simple, just sort all the edges in the ascending order. Then the selection criteria of the greedy algorithm is we have to look for the least cost and we have to add that into the spanning tree, provided if it does not create any cycle. So, let us try. So, 1 is the minimum, then look for the minimum, 2 is the minimum. So, I can add this because there is no cycle created, then next is 3, then 4, so no problem, 5 is also not a problem at all. So, you can see that 7 is also not a problem, 8 we can add because it does not create any cycle, but 9 we can't add because it can create cycle actually. So, 10 we can't add, so 12 we can't add, so 13 is possible. So, now you can see that this is the spanning tree that we have. This is another example. Again you can quickly go through the animation. So, wherever we have the least cost, we are adding that. So, whenever the addition causes the cycle, we stop. So, you can see that it looks for least cost edges, then finally you can see that the total cost is going to be 37. So, this is the answer for this. So, we have to implement this. How to implement this? For implementing this, we need to find the edge of the lowest cost. So, we will be using a data structures called a disjoint sets. So, the logic is very simple. So, I am making all the nodes as individual sets, then I am going to sort everything. So, I have to see whether it forms cycle or not. This is the toughest part. Fortunately, disjoint set simplifies this problem. So, I can use the find set u and find set v. If these are not equal, that means they are not forming any cycle. So, I can add this edge. So, I can go for set union. So, repeatedly I can iterate this. Finally, at the end of the algorithm, I have what you say, the spanning tree. So, what is the complexity of this algorithm? The complexity is dependent on the complexity of your disjoint data structure. So, the running time is order of v plus e log e plus e log e. So, that means you can see that if E is order of v square, then we have what you say order of log v. This is the complexity of this particular Kruskal algorithms. The next algorithm is Prime's algorithm. So, this was designed by the person called Robert Clay Prime. So, again he is a American mathematician, computer scientist. So, this is the informal algorithm. So, you can see that it is exactly similar to the earlier Kruskal algorithm. Initially T is going to be having a single node. So, that means we have to start somewhere. We can start anywhere in Prime's algorithm, and E is nothing but the set of edges that are adjacent to S. So, I am taking the edge and I am checking whether it is already there. If so, I am going to discard, otherwise I am going to add that. So, this is the informal algorithm of prime. So, let us try to apply that to this particular example. So, we will start from here. So, I have to look for the minimum cost. So, 4 is the minimum. Now, I can have two possibilities. I can check all edges that starts from A as well as B. So, I will just branches out. So, it is C. So, now I have the possibility of A, B, C. So, I can find the minimum. So, it is 2 now. Then again I can check the minimum cost. So, that means you can see it is going to be the 4. So, now again I can check it is going to be 2 and again it is going to be 1. So, you can see that I can't add from H because it may create a cycle. So, that means it is going to be 7, then you can see it is 9. So, you can see that this is a spanning tree that I am getting. Okay. So, you can see that all the nodes are present and you can see that this is the lowest cost spanning tree. So, this is a informal algorithm. So, I will be what you say using the heap for this particular algorithm. You can see that initially I will take all the vertices. So, initially key is assigned as infinity. So, I am going to extract the minimum, and for every adjacent I will take V I will take and I will check it. So, you can see that accordingly it is added. So, that means you can see that it uses the priority queue. So, each object in queue is the vertex. So, I am taking the key which is the minimum weight of any edge. So, you can see that the vertex that is returned by the extract minimum is such that it is belonging to U, and it's the light edge crossing from V A to V minus V A. So, that means we can use the key attribute of the priority queue to use in Prime's algorithm. So, what is the complexity of Prime's algorithm? Complexity of the Prime's algorithm is very simple. For initialization, it takes order of V. Then for building the initial queue, again it's order of V. The main component of the algorithm is extract min. So, the complexity of that is order of V log V. Then key manipulations, for that decrease key, it is going to be order of E log V. So, that means put together you can see that it is coming as order of E log V. If you are going for Fibonacci heap instead of the binary heap, you can see that the complexity is coming as order of E plus V log V. This is a complexity analysis of the Prime's algorithms. In summary, we can say that greedy algorithms are very useful for solving optimization problems. Spanning tree is one of the most important problem. MST has got wide variety of applications. So, solving those algorithm using brute force is very difficult. Therefore, we are going for two greedy based algorithms, Kruskal and Prime. MST has many practical applications, especially in network and all. It can be used to optimize the network. Thank you very much. In this module we discussed about two important algorithms. Next module we will continue some more examples of greedy approach. Thank you very much.